When I was invited to present at this conference, the intent was to provide the audience with a view of upcoming technologies for detecting PFAS. Since that's what we were doing at Fluorityx, I got very excited at the opportunity. Then I got very nervous. I've sat in your shoes as an audience member, and I didn't want it to just be perceived as just another commercial. Also, this is our first public conference, so I thought instead I'd talk about the current state of PFAS measuring capabilities and what current gaps exist. Does it support the ultimate goal of no PFAS exposure to the population? Thinking through this, I ended up developing a simple framework that I'd like to share. So in the next 15 minutes, I'd like to share with you how I developed this framework and relate it to PFAS measuring, then share what progress is being made regarding advancing PFAS technologies, and then how you can help. It is my hope that by the end of this presentation, I've convinced you that utilities need more tools than what's available today to measure PFAS in drinking water. I wanted the framework to be valid across multiple situations, so I thought I'd start with something that is commonly measured in drinking water systems: free and total chlorine. Chlorine is a very important chemical in drinking water systems, and there's many ways to measure both free and total chlorine. Here's an example of 4 different systems that I've discovered: ICP-MS, a lab-based instrument, a common test kit, a calorimeter, and a multiplex system. This system here measures pH, free chlorine, flow rates, you get the idea. And with these different measurement tools, each one has a particular characteristic, and that's both common and different across them. The ICP-MS is very highly sensitive. It can be very selective. The test kit as well, you take it to grab a sample. It's there on site. You can do both free and total chlorine. The calorimeter as well, you can grab a sample, measure it on site, and there it is much more sensitive than the test kit and is selective. On the multiplex system, it does perform on site. It's rapid, sensitive, but it is not selective. It does not measure both free and total chlorine. So looking at these characteristics and having those in mind, I developed a framework using a Venn diagram. Each circle represents the characteristics I realized. One, you have the selective instruments that are selective, you have a set of instruments that are rapid, a set of instruments that are sensitive, and then those instruments that you can perform on-site measurements. So with that framework in place, I also wanted to capture the underlying motivations for using the different pieces of equipment. And what I discovered seemed to fit well with regulatory controls and assurance. Those characteristics on the left-hand side, selectivity, sensitivity, seem to align with wanting to have the right measurement, very specific for the exposure to or for the reason for the regulation. If you look on the right-hand side of the diagram, rapid and on-site, those support more operational controls. You have a lot of flowing water going through your system. You want to be able to understand what the quality of that water was at that time, so you could make operational changes, chemical changes, whatever you need to do to help support the operations of your system. So after putting this together, I did realize that there is another important motivation that's missing. Where does health and safety motivations come into play? What types of instruments are ideal for supporting health and safety objectives? So for me, I would argue that it comes in the middle. You want both the ability to be very selective and sensitive for what you're trying to measure, and then also to have that measurement rapid, available, and ideally in line on site, so you can make any changes again to protect overall health and safety. So if we look at the chlorine instruments, I've placed them in the Venn diagram. You can see that the ICP-MS is selective and sensitive, the test kits on site and selective. So I couldn't find an instrument that exactly supported the ideal scenario of health and safety objectives, but it's good to have a toolkit of options that the industry can use to help support health and safety requirements. So let's shift to PFAS. What does it look like today? Now, before we go there, I do want to make sure that we are aligned on the characteristics. Before I'd label them, you could say they're subjective. To make more of an alignment on how I'm using this diagram, we should make the characteristics more quantitative. And so for selectivity, I will call that it's specifically needs to be able to speciate the molecule. So for PFAS, we want to be able to measure not only PFOA, PFOS, Gen X, etc. For sensitivity, the target is less than 10 parts per trillion. So an instrument that can record incredibly low levels of PFAS will help support because they are aligned with the EPA regulatory minimum control limits. On the operational side, we want to be able to take a measurement within 5 minutes so we can see at that point in time what the measurement is, and then on site, having it close to where you're pulling the sample or even during the inline so that, again, that piece of water that you are measuring, you have assurance that that's what the level of PFAS is. If we are waiting too long for PFAS to be measured, water is flowing at millions of gallons per day. You could take a very long time and a lot of water going through your system before you even know what it was, and by then it's too late. Okay. So as of today, the main method for measuring PFAS is through an instrument called liquid chromatography mass spectroscopy, LCMS for short, and that's it. And it is a lab-based instrument. It is ultra sensitive. It can detect very low levels. However, the protocols for preparing the sample are very rigorous, requires a lot of different consumables, a day to prep the sample, and you can't do it on site. You have to send it to an in-house laboratory or shipped the sample to a third-party service provider. Of course, it's not a surprise that the regulatory requirements are aligned with the LCMS's capabilities. It can measure multiple PFAS molecules, many more than what are currently regulated for, and its detection limits are extremely low. Of course, the closer you can get to the contaminant goal, the better. This table was taken from the EPA website. You can look at the methods for drinking water detection. Those are the EPA methods, 533 and 537.1. But again, the LCMS was the chosen instrument to be utilized in the protocols that were developed for PFAS detection. Now the problem, as I hope you can understand, is that there are many utility drinking water systems that need to control PFAS. And even those that are today below the limit may be above the limit tomorrow. So there will be a consistent need across thousands of different utility systems to measure PFAS. And then secondly, there are different abatement technologies that exist today, but there are new ones that are being developed as well. But as you can imagine, if you have to wait a long time for the result to see if the technology is working, it is very difficult to commercialize these technologies. So my argument is we can't expect LCMS to be the only instrument to do it all. Operations needs something that's quick and rapid, and I'd argue that if we want any chance of achieving no PFAS in drinking water, we need new tools to complement LCMS that support the objective of keeping our population safe. So the good news is help is on the way. I have in my presentation 5 companies that are working on solution. The first 2 is a company named CSAWWA. They're based in Georgia, and they're leveraging some technology developed out of Georgia Tech. You can go visit their website to learn more. Also, FredSense Technologies, based in Alberta, Canada. They are also have their existing platform and have published some case studies. You can see them on their website. Third is a company called Graphil in collaboration with the French laboratory, governmental laboratory Editem. They've developed a credit card size detector. Again, you can find more information on their website. And then another company called Wave Illumina, who's based in Michigan. They do not provide a limit of detection, but they do claim that it is a contamination field screening device. Again, please go to their website. What I can share with you is what we are doing at Fluorityx. So Fluorityx uses an amplifying fluorescent polymer as our way of detecting PFAS. This technology has actually been commercialized and used in industry for over the last 20 years. And the original use was for detecting explosives, came out of MIT, used today. And what's amazing about this technology, you can put it on a robot, you can put it on a handheld device, is it meets that sweet spot right in the middle. It's ultra sensitive, it is rapid, it is definitely on site, and very selective. So here's some of the theoretical foundations of how the amplifying fluorescent polymers work. I'm not a chemist, so I won't go into detail for you, but if you'd like a more detailed explanation, there is a link in the lower left-hand corner of the paper published by MIT and the experiments conducted. I can say that on the left-hand side, the way the polymer was reconfigured was deliberate to be specific to have an affinity towards PFAS molecules. And on the right side, it shows that the gain mechanism works when ultraviolet light is shown on the polymer surface, and its emission changes when a PFAS is absorbed into the polymer. So both of those things make it selective for PFAS and highly, highly sensitive. When we've taken this technology and transferred it into the Fluorityx lab, we've had some success. We've coated the polymer on some glass slides, and on the picture on the left you can see that the glass slide that did not have exposure to PFAS shows a blue emission when you shine an ultraviolet light on it, and when it was exposed to 10 parts per billion of PFOA, it changed its color. On the right hand side you can see that the spectra is changing with increasing levels of PFOA chemicals. And so what our first generation instrument will be designed to do is measure the change in the ratio from the peak, as you see, that's decreasing with increasing concentration between the 400 and 450 wavelength, and the increase between 500 and 550. We'll measure that change, and that will provide us an indication of how much PFAS is in the sample. So here's preliminary results in the laboratory. What's exciting for us is that the glass slides that have the coated polymer on it were only exposed to a sample for 25 seconds. And you can see, although there is some noise in our results, our signal shows a step change between the control and 0.1 parts per trillion, and different from 1 part per trillion and higher. So we're very excited about this technology. We've got a lot more to do, a lot more things to test with, but we are excited about these results. We've actually tested this with real AFFF contaminated groundwater, and before and after it was cleaned, and it measured in the ballpark. So we are very hopeful about improving the noise and making this a more usable instrument for PFAS detection. We have been invited to participate in a drinking water pilot program with Kimberly Horn. This presentation we've been invited to participate in a drinking water PFAS pilot program from Wigwam Mutual Water Company. The purpose of this pilot project is to test the differences between ion exchange resin, granulated activated carbon, and electrocoagulation. The opportunity for Fluorityx to participate is having our sensor to measure the influent groundwater that was contaminated and has some PFAS in it, as well as testing the effluents of those three systems. So we are excited to be able to compare our results on real world samples. So to wrap this up, here's where our Gen 1 system currently looks like. We will have a system that's rapid. We'll have a system that you can use on site. It will be very sensitive. We don't have the ability yet to be selective in measuring the differences between PFOA, PFOS, Gen X. We can report on a PFOA equivalent, but samples with mixtures, it'll be an aggregate result. So we are working towards second generation systems, instrumentation that will allow us to provide more speciation, and that's definitely in our sights in the future. So what can you do? I do believe that utilities need a larger suite of instrumentation to measure PFAS to create healthy outcomes. If you go to our website, you can find a sign up section to be on our waiting list for when we are able to release our first generation system. You can also follow us on LinkedIn for news and updates. But I think overall in general, what companies like Fluorityx and the others that I had mentioned on the slides is just having dialogue with us, sharing feedback on what characteristics are most critical for your needs would be extremely helpful. And then being open to participate in demonstration pilots. The more we can get the opportunity to bring our systems to increase the technical readiness level, the quicker we can get it out into the world. So thank you very much. I appreciate you taking time. This QR code will take you to my contact information. Feel free to reach out if you have any additional questions.